Okay, so this is Edward Doolittle again. Finally, last section of the textbook we're covering in this course, 11.3, ANOVA, the one-way classification. And we've already talked about the introduction to ANOVA concepts in 11.1 and 11.2. Here we're going to turn to the actual calculations, really the important part of this. So one-way classification means that there is one factor. And that's all that we're going to do in this course, one factor. We have to either assign or find a sample, a random sample. So if our factor is gender, then we randomly choose n from each. That's for gender or for height or for some other observational characteristic. On the other hand, many experiments have we don't have the categories determined in advance, so we apply a treatment. So a drug, a vaccine, a pesticide, that sort of thing we apply. This is for observation. So in observation, it's very easy. We just randomly choose n from each level. But for applying a treatment, we apply the treatment first. And that application has to be random. I should say which treatment. Treatment chosen should be random. So, for example, if we are applying pesticides to a plant, we pick a plant, we randomly select which pesticide to apply. Then the next plant over, we randomly select which pesticide to apply. We just don't want any patterns in the pesticide that we choose. So we don't want the first block of 5 plants to have one pesticide and the second block to have the second pesticide and so on. There should be mixing. So these are kind of basic assumptions here. In any case, the factor will have k levels. This is to make it general. For us, it will often be k equals 3, often. It doesn't have to be, of course. We could have 4 levels, we could have 5 levels, whatever. But this letter k is going to be reserved in all of our following discussion for the number of levels. In the lunch example or the breakfast example that we had no breakfast, we had a light breakfast, and we had a heavy breakfast. And that is 3 different levels of this breakfast factor, so k is equal to 3 in this example. And as I mentioned in the last lecture, our hypotheses are alternative hypothesis 1 of mu I differs from the others. And our null hypothesis is that none of them differ, they are all the same. I is used as an index to refer to the treatment level. I varies from 1 to k. So I may go all the way up to 3. It starts at 1 and it goes up to 3 in this typical example. I can also vary, if there were k, if k was 4, then I would be between 1 and 4. And so on. So I is just an index letter that varies from from 1 to the total number of treatments. Okay. We have to be a little bit careful about indices in all of this. That we're going to make more use of indices than we ever have in the course before. Because usually we were working on, we just had one kind of index, one thing varied. But in this, we've got two things that are varying. So one is the treatment that is applied. And the other thing is the measurement, or the individual within our sample. And that can vary from 1 to whatever the total number of our population, or sorry, not our population, our sample size. So our sample, for each of these populations, we're going to take a sample, and the sample size may vary from one sample to the next, or from one treatment to the next. And so we're going to have to give that an index. And just this should remind you of what happened in Chapter 9 when we had two populations. We had sample size of sample 1 was n sub 1, sample size of the second sample was n sub 2. In this case, we will have, since we're often working with 3 populations, we will have 3 sample sizes. It's helpful if these are all the same or very close to each other. The mathematics tells us that our test is more robust if these numbers are similar or the same. But they don't have to be. We just have to pay more attention to the rest of our assumptions if these numbers are different. And so within this population size, let's say I had 10 in the light breakfast crowd. I had 10 in the, this is the no breakfast group. I had 10 in the no breakfast group. I had 10 in the light breakfast group. And in the heavy breakfast group, I had people fainting because they ate too much, so I ended up with just 8. So that could be possible. And then here I have J is 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, all the way down to 10. Here J can vary from 1 to 10, and here J can only go from 1 to 8. So in this sample, there are fewer experimental units, fewer individuals, so I can my index, this J letter indexes or gives a number to each of these participants. It only goes from 1 to 8 in this sample, but it goes from 1 to 10 in the others. Okay, so that's what J means. J is context dependent. It depends on which population we are examining at the time. So that, I hope, at least helps to set some kind of framework on this. We have 2 indices in this investigation. One is I. I indexes the treatment, and J indexes the experimental unit or the individual within that treatment. And so if I want to find out if I want to know the response of the third person in treatment group 2, I say treatment group 2, third person. And so that's not 23, but that's 2, 3. And that is the measurement of the response for the third person in the second group. Okay, so that's what our indexes mean. That's how we interpret our indices. We are making another assumption, and that's that the variances for these populations are all the same. So the shapes of the normal distribution curves will be the same. And here these two are so close, they overlap so much that it's hard to distinguish between them, but this one is going to look is very different from the others. And so that's what ANOVA is going to try to detect. Is one of these things not like the others? In other words, is its mean far from the means of the others? In that case, then the treatment does make a difference. And we detect whether there is or isn't enough space between them to declare that there is a real difference in the populations based on what we see in the samples. But we do have to assume for ANOVA that the heights of these normal distributions, the variances of the normal distributions, are the widths of them, basically the size of them, are the same in each case. Okay, so that dispenses with all of the preliminaries. Now let's turn to some of the formulas. So the first thing we're going to look at is this thing called sum of squares. And this is the sum of squares of the deviations from the mean. So what I do is I measure the mean of all of my respondents. It doesn't matter what what treatment they're in. I just take all of my everybody who participated in this study and average them together. And that gives me an overall mean. And then I take each individual and compare them to the mean. And I square those differences and I add them all up. So that's what that formula means. It's the sum of the squares of the deviation, I should say. The sum of the squares of the deviations from the mean. And this is exactly, if you think back, this is exactly how we calculated the variance for a sample in Chapter 2. This is the definition of the variance for a sample. Now, this turns out to be a little hard to work with, so we're going to split it into two parts. And just like we did with the computing formula for the variance, we can just take the squares of all the measurements. This is everybody in each treatment, each individual in each treatment, and I just square them. And then I can, from there, subtract. If I add them first, and then square that. So here I square first, and then I add. And here I add, and then square second. And then I divide that second term by n. And again, this should look very familiar to you. This should remind you of the computing formula. For the variance that we learned way back in Chapter 2. All right, so that is our kind of initial important concept, is this total sum of squares of the deviations. All right, now this second term will appear a couple of times in our calculations. So what we're going to do is give it a name. We call it correction for the mean. And CM is the symbol. And just to repeat myself, I'm going to rewrite this ij over n. So it means I add up all my measurements, I square that number, and then I divide by n. That is CM. This adding up all the numbers, we call this sometimes the global sum. So that is G, is the global sum of all of my responses. Okay, so the magic now is when we partition our SS into two parts. The sum of squares for the treatments, and the definition of the sum of squares for the treatments is all right. So this is the mean within a treatment. So here, what I'm doing is I'm taking all of the measurements just within a single treatment. I'm making the mean of those measurements, and then I'm subtracting that from that the overall mean across all the measurements. So this gives a kind of variation for the, or deviation, I should say, with respect to which treatment we're looking at. So as I varies, this moves from one treatment to the next. We are weighting those measurements by the size of the pool, the sample size, and we're just adding those things up. And that thing is altogether called SST. Now we're going to need one more notation here, and that's that TI is the sum of the sum of all the measurements. Here I is fixed. I fixed. So in other words, T1 is the sum of all of the responses in treatment 1, and T2 is the sum of all the responses in treatment 2, and so on. Okay, so that is the meaning of that notation, and with that we have another way of calculating SST. Again, this is really basically the same as a computing formula, and that is the sum over all of the subtotals divide that by the size, and then we have to throw in that CM, correction for the mean. And this is just algebra. We're not going to look at all the ins and outs of the algebra. But if you had to calculate this by hand, this is the formula you would use. This formula appears in the formula sheet, so you could potentially calculate these things by hand if you ever need to, but you generally won't have to. I will explain to you why in a moment. Okay, finally, last one, the sum of squares associated with the error, and that is a very difficult formula to calculate. So this says for each of our treatments. We're going to take the pool, the number of the sample size for each treatment, subtract 1 from it, multiply it by the standard deviation for that treatment, or not the standard deviation, but the standard deviation squared, the variance, in other words, the variance for that treatment. So here's the variance for the first treatment multiplied by the size of the sample size minus 1. We add up all those things. There is a large a lot of algebra that you would have to do, but it turns out that we have partitioned our sum of squares into 2 parts, SST plus SSE. So the sum of these 2 complicated formulas adds up to our SST formula, adds up to our SS formula, which was the one we started with on the previous page. Okay, so that is a crucially important property. This is the most important thing about the sum of squares, is the fact that SST and SSE add up to make SS. So if you know 2 of these guys, you can figure out the third one. And out of all of them, this one is by far the hardest to calculate. So you can save yourself that serious effort of calculating SSE just by calculating SS, SST. Then SSE is SS minus SST. That's just a little, very simple piece of algebra from here to here. Okay, so that will save us some work. In a test situation, an exam situation, I'm going to save you even more work. I'm not going to ask you to calculate these. I'm going to give you SS and SST, and then you can figure out SSE without much fuss based on this formula. Right? So, I could easily ask you to figure out what SS is from this formula, and then I could ask you to figure out what SST is from this formula. It's not that hard, but it's just something that will take more time than it's really worth on an exam situation. And I know some people are not really great with these kinds of formulas, so I'm not going to ask you the question that way. I'm going to pre-compute these things for you. So you can rest assured that any question you're going to get on the exam, I am going to pre-compute SS and SST for you. Or I might even compute SS and SSE, or SST and SSE. Anyway, two of these 3 I will give you. You might have to figure out the third one, but you can do that by using this extremely simple formula. Okay, so that's my deal with you for calculating the SS's. Now, there's one other kind of basic concept that we need, and that is the DFs, degrees of freedom. So we talked about this in our chapter 10, when we were talking about small samples, the student T distribution. The same kind of general idea for ANOVA, but it's complicated by the fact that we have now multiple different different treatments, different levels. So DF, the overall formula for DF is the same as it was in chapter 9. It's or chapter 10, pardon me. It's n minus 1. So the total size of our sample, meaning all overall, including everybody from all treatments, is n. And then we subtract 1 from that and get the number of degrees of freedom for this investigation. Now, there is another concept of degrees of freedom here, and that is, so we're going to call this degree of freedom total. We also have degree of freedom among the treatments. And in this case, it's k minus 1. Finally, degree df of the error is a complicated formula, but bottom line, it ends up being like this. So this is hard to explain without going into a lot of details that we skipped in chapter 10. We skipped why this is calculated the way it is. You can see some derivation of it in the textbook. All that matters to us is the bottom line, the final formula in each case. And you'll find these formulas in your formula sheet. All right, so that kind of completes the preliminaries. And now we're ready to put this all into a table. My table, I'd like to draw it a little differently than the textbook does. And I'm afraid I'm not sure if I fixed this table in the on the website. But anyway, I'll do it the way I like it, and you can choose however you like to do it. There isn't that much choice, but there's a little bit. So variance is what we're talking about here. ANOVA, analysis of variance. And there's two sources for variance. There's the treatments, and there's error. So error comes into every experiment. Error is just random variation that we have no control over. Treatments are what we do have control over. And then there's total error, or total variance. Okay, so a couple of things are going to be split this way. First thing is the SS, sum of squares of deviations. It gets split into two parts, the SST, SSE, and total SS. Okay, and so I gave you formulas for each of these, but I told you in a test, in an exam situation, you won't have to use those formulas. I will supply you with the necessary tables. Necessary pre-computed value in the table. So I will give you these numbers inside this table. At least two of them, anyway. You can figure out the third from knowing two of them. Next thing I like to put in this table is the DF's, degrees of freedom. So the degrees of freedom among the treatments, we wrote down that up here. So I'm just going to fill in that formula. K, remember, is the number of different treatments. It's typically 3 in examples that we look at, but it could be 4, it could be 5, whatever. We found that this was n minus k, and there's a reason for that I didn't go into. You can read something about it in the textbook, though. Finally, if I add these two numbers up, I'm going to get k minus 1 plus n minus k. I get n minus 1, which is exactly the total degree of freedom. So there's this nice relationship that SST plus SSE equals SS, and k minus 1 plus n minus k equals n minus 1. So my table, I should be able to sum the first two items and get the third. And that applies to both of these columns, the SS column and the DF column. I don't like that. Okay, next we're going to calculate the mean. The mean sum of squares. And that's where we divide we divide these two. So that's why I like to put them in this order, because that tells me what order to divide them. So MST, the mean squares of the treatments, is SST, the sum of squares of the treatments, divided by the number of degrees of freedom. So that's K minus 1. And the mean squares for the errors is the sum of squares for the errors divided by the number of degrees of freedom. Okay, so that is a MS column. There is no sum down here, so this is just nothing. It doesn't make sense to add the means up. And finally, there's this quantity mysteriously called F. I will explain that in a second. F is MST divided by MSE. Okay, so this table is now complete. This is called an ANOVA table. And it's easy to remember how to put it together. The first two columns I add up. So the first number here plus the second number equals the third number. This number, and this number add up as well, but they have formulas. We know K is the number of treatments and N is the total number of experimental units across all treatments. Once we have these, then we divide them in this order as we take the first thing in this row divided by the second thing to get the third. And the same in this second row. I take SSE, I divide by N minus K, I get MSE. So that gives me the numbers that go here and here. Finally, I take this number, top number, and I divide by the bottom number here, and I get this F number here. So there's a kind of mnemonic about how how to put this table together. Once you've done a couple of them, it should become second nature to you. Okay, lots of formulas, of course. You could find, the boxed section in the textbook gives all the details about all the formulas. All that we really need out of all the formulas is a way to calculate two of these three. This one and this one would be the easiest, and I will typically just give you the numbers. I won't ask you to use formulas to calculate those things. Okay, anyway, what is the big deal here? The F is the big deal. F has a certain distribution. F has a F distribution. And this is just theory. We're not going to go into, but it's something like the central limit theorem, although it's not the same. Anyway, it leads to, under sort of ideal conditions, that F that we obtain here is a random variable. We will get different numbers depending on the samples that we choose. But overall, across all the samples, it will have this kind of histogram. So this is a histogram for F. F is always a positive number, so it cannot be negative. So this kind of histogram, or this distribution shape, differs from the ones that we've seen before. The normal and the T distributions we've seen before have gone to infinity on both sides. This one goes to infinity only on the right, because I cannot have negative values for F. So it starts at 0, and then it goes to infinity on the right. Otherwise, the kind of the general idea how we use this F is very similar. One other thing about F is there is a family of distributions, very much like the T family of distributions. If you recall, there are different T's corresponding to different degrees of freedom. F is just a little more complicated in that there's different F's corresponding to the 2 degrees of freedom. From this formula, from this table. DF1 is the first number and DF2 is the second number on the table, associated with the degrees of freedom for the treatments and degrees of freedom for the errors. So That these two numbers give us an index into which F distribution is the right one. Then there would be a whole book full of different F tables, just like there could be a whole pamphlet full of T tables, depending on varying as by their degrees of freedom. So since there are so many different F distributions, there are literally thousands of them, we are not going to tabulate the entire distribution. We are only going to tabulate the critical values. And this is exactly what we did with the T distribution as well. There are so many T distributions, 30 of them, that we would typically need to use, that we gave up on making a 30-page pamphlet of T tables. So we just gave critical values. And the same for the F distribution. There's many more than there were T's. There would be a whole book full of F distributions, and we are only going to give critical values. Okay. Let's now finish this off by giving an example. So we have example 11.4 in the textbook. Experiment to determine the effects of nutrition on the attention span of elementary school students. This is, I don't know, sounds like the most horrible experiment. As a member of the Research Ethics Board, I don't know if I would give this ethics approval. What are we going to do? We're going to starve some kids, give them no breakfast, and then give them tests. Anyway, it sounds awful, but let's soldier on through this example. So a group of 15 students were randomly assigned each of 3 meal plans: no breakfast plan, light breakfast, and a full breakfast plan. Their attention spans were recorded during a morning reading period. And then we're going to do the ANOVA table. So we have the raw data, and 8, 7, 9, 13, 10. Light breakfast, so this is no breakfast, light breakfast, or full breakfast. Here, 14, 16, 12, 17, 11. We have 10, 12, 16, 15, and 12. Okay, we can work out the sum of these columns. I'm not going to ask you to do that when I give you an ANOVA question, but I just want to show you that it can be done. Then we're going to settle with some parameters here. What is K? K is the number of treatments. That's 3, because you can have no lunch, you can have or no breakfast, a light breakfast, or a full breakfast. That's 3 different treatments. We have the sample size for sample 1 is 5. For sample 2 is also 5. For sample 3 is 5. Those are all equal. The total number of participants is 15. And then the global sum is 182. And that I could get by adding T1 plus T2 plus T3. Okay, so once I've got all these numbers, I can figure out easily what SS is. And I will do this sort of thing for you, so you don't have to do it. And this time I'm going to give you, or I'm just going to grab it from the textbook. So total SS is 129.7333. Okay, similarly, I could work out what SST is using formulas that I've given you, but I won't ask you to work it out. I will just do it for you, and it's going to be 58.5333. And this should be enough to get us started, so let's start building this ANOVA table. Source, there's treatments, errors, total, We're going to look at the sum of squares. Oops. So total is 129.7333. The treatments was 58.5333. So that gives us SSE. We can work out by taking the difference of those two. It should be 71.2. There's a formula for SSE, but it is awful to execute. It's much easier to get SSE this way. Okay, next, degrees of freedom. These are just formulas, so k minus 1, k was 3, so k minus 1 is 2. df for the error is n minus k, which was 15 minus 3 is 12, and df total was n minus 1, 15 minus 1 is 14. Notice that these numbers add up as well. Okay, next I want the mean sums of squares. So I just take 58.5333, divide by 2, and I am going to get MS is 29.27. Here I'm going to get 71.2 divided by 12, and I'm going to get 5.93. Finally, F is going to be 4.93. Okay, and that is our completed ANOVA table for this example. Now finally, we're going to use the F to do our hypothesis testing. We're going to use a critical value method, just like we did with the t-test. There's also a p-value method, which we are not going to do. It is important to do that, but I would just use a computer to calculate p-values, just like with the t-test. So when we're doing it by hand, we're going to stick to the critical value method. Okay. So for the critical value method, remember, we should remember what our alternative hypothesis is, at least one mu I differs from the others. Our null hypothesis is that all the mu i's are the same. That looks kind of messy. I'm going to fix that. There. That all the mu i's are the same. We have calculated the test statistic. So that's step 1, step 2, step 3 is the test statistic. F is 4.93. So that was that whole ANOVA table. That was the whole point of the ANOVA table, was to calculate the test statistic. For the critical region, we have to use our F table for this. So there's an F table that I have included in the chapter 11 handout section, and there's also a little package. It's all been packaged together nicely for you in the final exam review section at the end of the course. You see all the tables put together into one little package, PDF package. So in there you'll find your F tables. We use the numbers in the F tables to find the critical region. Before we do so, we have to figure out what our 2 degrees of freedom for this problem are. df1 is 2, df2 is 12. Okay, now let's pull out our F table. I'm just going to use the one in the textbook. This would be Appendix 1. Okay, Appendix 1. table 6, I believe. It is a big table. And it is hard to read. So we need to learn a little bit about how to read the F table. So there's Appendix 1, Table 6 on page 725. We are going to go across the table and look at the DF1 is 2, so that is the first column. And next we're going to go down, DF2 is 12, so we have to go on to the second page for that. Third page, sorry. We're going to look at the third page, so we've located a DF1 is 2, DF2 is 12. Finally, one other thing that I forgot to mention is that, of course, we need to know alpha for our test. And I haven't specified alpha, so that means we're going to use alpha is 0.05, as always, if I don't specify it. If I do specify it, you have to look up accordingly in the table. So you'll see that each kind of row of this table is divided into 5 sub-rows corresponding to our commonly used values for alpha. Alpha is 10%, 5%, 2.5%, 1%, or 0.5%. So we've chosen alpha is 0.5%. So the correct number, and you should be able to find this on your table, is 3.89. So that's the second column. The column labeled DF1 is equal to 2. And the 12th row, that is DF2, is equal to 12. And then in the sub-row corresponding to 0.050, we read that corresponding number and it should be 3.89. So this is a skill that you need to practice. You need to learn how to use your F tables. So the critical region, critical value, is 3.89. So I'll draw my picture. All the F's look the same roughly. The details are different, but the general shape is always the same. 3.89 is the critical value for F. The acceptance region is the region that includes 0, as always. The rejection region is the other region. Where is our test statistic? It was 4.93. It is in the rejection region. So, conclusion, reject. Oops. Okay, so finally we'll write the conclusion in normal language at the 95% confidence level. We conclude that at least one of the means for the treatment groups is different from the others. That's it. We're done. That is all that we can conclude. We don't know which one is different. Now, you may look at the data and speculate. Proper way to do that is to use an ad hoc, is to use a post hoc analysis. And there are some tests given in the textbook. I am not going to put them on the exam, so just forget that post hoc analysis. We're not going to do it. We're not going to be able to tell which one is different. All that we know is that there is one of them is different. And this means that we need to do more work. Which one is different? How much different is it from the others? Can we quantify these things? But that is work for another day. All right, so that's it for the course. That is the picture here with ANOVA. It's a very simple version of ANOVA. It's the most basic version of ANOVA, just to give you a sense of how ANOVA works. And then you may need to learn variations on this depending on what kind of what you go into. This is especially for nursing. It's important. Lots of experiments in nursing use this kind of multi-factor design, and so you will have to probably, if you go into nursing, look at look at variations of this ANOVA. But this is the most basic one, and is certainly opens the gate, opens the pathway for you to learn more about it. One last thing I wanted to say, how important the p-value is. I've said this, it's really important. It's just that, again, we don't have the computational power to calculate the p-value, but the p-value in this picture would be this area here. And so we would need tables, better tables than we have to calculate the p-value accurately. Most of the time, instead of using tables like that, we would just use a computer to calculate the p-value. And so you'll see in this, if you go back to page 474 in the textbook, one-way ANOVA span versus meal, they've used a computer program, namely Minitab, to produce this, to produce the ANOVA table. And you'll see we have all the same numbers as the computer got. Even though we did them by hand, we got the same numbers, of course. The one thing that the computer got that we didn't is p. And so the p-value for this is 0.027. And if you are writing a journal article about your study, then you would have to include the p-value. And here we have a p-value which is less than alpha, which was 0.05. So this tells us, again, is another way to show that there is a significant finding here that we reject the null hypothesis. All right, so that's how the pros do it. You would use a computer program. You don't have to buy Minitab, though. If you really want to do this, you can do it with for free with R. I use Excel often to calculate ANOVA tables, and I'm not sure if you can use Google Sheets or not. Don't know. Excel is dead easy. You just put in a couple of numbers, your data, not a couple of numbers, but all your data, your 15 numbers in this case. You type in your 15 numbers into a nice table. You then hit a couple of magic buttons in Excel, and it produces the ANOVA table on another spreadsheet. Anyway, that's it. I hope you have a good Easter break, so please take a break. I will, at some point over Easter weekend, post our last quiz. It'll be based on chapters 9 and 10, and it'll help you study for the final exam. And then our final exam is at the usual time. It will be an online exam. I plan to make 10 questions, each worth 1 point, to give you an exam worth something out of 10. And there'll be some calculations involved in each of those questions. All right, so we'll post more details about exam and quiz as those things become ready. I'm sorry I'm a little bit behind with the, it's taken me a lot of effort to produce these online materials, so I'm moving a bit slowly with it. But anyway, I hope you do enjoy your Easter break, and I will see you all soon. Please